Our next speaker is Dr. Timothy Hall from Faraday Technology. He will be presenting, he will be presenting ionic liquid assisted electrochemical extraction of oxygen from lunar regolith.
Hello, everyone hear me?
Yes, we can.
Awesome. So today we're going to talk about phase one SBR program we had with NASA that we were looking to develop a way to use ionic liquids to dissolve regolith and recover the metals from a regolith by electrodeposition. Next slide, please. So I think the space challenge is pretty well understood that if you want to habitat on the moon or Mars, you need a way to use the resources available and also enable life support of oxygen and water. Next slide, please. So looking at the regolith complex from the on the right, you can see that the majority of the oxide is bound up in silicon and aluminum with some other small components in calcium, iron, and manganese. So the goal of the activity was to be able to take surrogates. In our case, we first wanted to focus on silicon or silica, such that we can recover the silicon as a metal while also separating the oxygen and electrolyzing it to form oxygen for other uses. NASA specifically was interested in producing large amounts of oxygen, specifically for liftoff and other applications, not just life support, but you can imagine this through a broad range of things. Next slide, please. So the overall goal is to demonstrate an ionic liquid approach that you can continuously add regolith to, recover metals, and outgas oxygen. Go to the next slide. So this approach, as sort of mentioned already, it was a two-step approach where we took silica and it was silicon oxide instead of silicate. We specifically chose silicon because it is the most complicated thing to recover. There's already been techniques developed for alumina and some other materials, and we envisioned that by going to alumina silicates and other things, once demonstrating silica should be a natural transition. So first, we designed an ionic liquid with our partner Roco Global that we could add silica directly to. It would solubilize the silica and bind it in the ionic liquid in the form of the hexafluorosilicic acid and water. Then from that solution, we were able to apply an electric potential and use an approach called liquid-liquid solid deposition, where we're able to reduce the silicon from the hexafluorosilicic acid as a silicon metal and recover both the silicon and the oxygen, and then enable the reuse of the hydrofluoric ion and the IL to redissolve more silica. Next slide, please. So initially we developed the IL. This was work done by Roco Global. That we went through about 6 orientations of the IL, really trying to understand how best to add the active species, the fluorine species, which helps rapidly dissolve the oxygen, the silica oxide, such that the silica is freed so you can electroplate it. So we found one that seemed to have a pretty low viscosity, had a pretty high solubility of silica, and it had and it didn't have any required extra additives. So if you go to the next slide, the IL also had a pretty high electrochemical window. The top left corner just shows the electrochemical window, where you have pretty good stability from at least -2 volts to 2 volts. So you have a pretty good window for your electrochemical reduction processes. The bottom is a TGA. The bottom left shows a TGA analysis, shows pretty good thermal stability, and the bottom right shows that it has pretty good hysteresis of its temperature cycling of its life, as long as you stay below 70 C. So I think one of the big things to focus on in this work is we're utilizing a liquid-based solution that is stable over a broad temperature range. We're operating at less than 70 C, so we're at near room temperature, and we're directly dissolving and recovering the silicon and the oxygen. Next slide, please. So this sort of shows the setup of what we were using. This was a phase 1 SBR, so it's a very small program. So we had a small beaker where we had ILs. I think we were using 2 cc's of ILs in all these experiments. The liquid solid process works by using a liquid gallium metal, which melts at about 40 C. And that liquid gallium metal enables the reduction of the silica into the silicon gallium metal, and then you can reduce the silicon from the gallium metal onto a metal substrate, which in our case was stainless steel. So the way the system was set up, it was in a bagged chamber that was oxygen free. We put an oxygen sensor right on the top of it, which had some resolution challenges, and then we reduced the silicon from the deposit while electrolyzing water on the anode. And with this, we were able to measure some oxygen change, and we were also able to observe silicon deposits. Next slide, please. So this just shows that we were able to see silicon deposits in the gallium. The gallium is the large silver thing. You can actually see the little black deposits. So what's happening theoretically from the literature, this is some work out of the University of Michigan, they talked about using silicon chloride. You actually get a first reduction step from a silicon chloride to a silicon solid. In our case, we're talking about a silicon fluoride to a silicon solid. Then it's incorporated into silicon galvanide. Then it reacts at the substrate, the stainless steel surface, and you end up forming silicon particles. All while at the anode, you're actually electrolyzing water. So simultaneously electroplating silicon and electrolyzing water. Next slide, please. So doing initial polarization scans, this is looking at the effect of ramping the voltage. The blue lines show the voltage that we applied. The orange line shows the response current, and the numbers represent the amount of oxygen that was released. As you can see, going from up to about 2 volts, you really see not a whole lot of oxygen released. As soon as you get to about 3 volts cathodic, you see a lot of water electrolyzing, and you see an oxygen signature, and you see a current signature. At above 3.5 volts, we started to see some degradation of the IL, where the IL originally is very clear looking, and after too high of voltages, so after using the IL to reduce the silicon and run high voltages, it actually ends up, its electrochemical window has been shortened by the addition of silicon into the matrix. So we're beginning to understand the operating parameters, the temperature limitations, and being able to reproducibly generate oxygen while continuously adding silica. Go to the next slide, please.
You have 2 minutes.
Awesome. So this just shows that we were able to recover oxygen at a pretty high efficiency, and we were also able to reduce silicon. I go to the next slide. So big picture, this is the carbothermal approach that people have been talking about a lot. Now, if you go to the next slide, you can show what we're proposing is essentially a continuous system that could work to simultaneously dissolve fed regolith in the ionic liquids. You could feed the ionic liquids to a belt assembly, which we call the electrobelt, that can continuously reduce the silicon, recover the oxygen, and produce products. Next slide, please. Just shows another version of the same thing, where you see the liquid gallium, you see the ionic liquid with silica in it, or regolith materials of silicon, aluminum, manganese, and iron. And then you're constantly electroplating, and then you're recovering it on a belt. So this metal can then be used for other things. I think the biggest thing to consider is this is electrodeposition. So silicon will electrodeposit at 1 over potential, aluminum 1, iron 1, and manganese 1, meaning you have the potential to potentially selectively segregate each of the elements within the regolith, such as you could reuse them for various applications, or you could specifically design mixtures of applications. So big picture shows a way to go straight from regolith to metals while recovering the oxygen, all at room temperature. Next slide, please. So that's just another view of the same thing, showing the oxygen capture tank, the feed hopper, and the metal recovery system. Last slide, please. Thank you. So overall, what we showed that we were able to initially scale an ionic design and scale an ionic liquid. We demonstrated on silica as a simple initial state at a 70 C operation, which we believe will also work at around 50 C. We developed a process flow diagram, and we have a vision of how we would want to continuously operate to recover both selectively recover metals and also recover oxygen from regolith materials. And last slide is acknowledgments. This was a NASA-funded program where Brittany Brown was the TPOC and Santosh Vijapur was the principal investigator. So we were excited to work on it, and we look forward to hearing of any questions from the team. Thank you.
Okay, thank you. That's interesting.